So guys, we'll be starting in a couple of more minutes now. We've got two wonderful presentations for you today. One is on additive manufacturing from Sean McConnell. Sean, of course, is part of our AM group and part of the advanced center we're setting up in Mullingar. He'll be telling you a little bit more about that. And then, of course, we've got Anna Rotondo, who's going to go through simulation, explain a little bit about that process, this whole very exciting space where you can impact and have a look at your organization, your layout, etc., and not spend money up front and still see the impact of the different queries that you can put into the system. So Anna is very excited. It's going to be part of that. We are 10:32. We'll give them another 3 minutes and then we'll get set up then for 10:35. We have a slow week, I think, with Halloween and all the kids off in school and all of that. John, I'm going to unmute you. John Carmody from EFC or Dell Corporation. John.
Yes.
John, you're with me, John. I'll tell you, I'm just doing a little bit of an interview here while I have you. John, tell me, are you interested in the additive side of the house, do you think, or the simulation, or both, or just having a look, see where we're at?
I think at the moment we'd be more interested in the simulation. The additive is a piece that we haven't got into, that kind of customization or that use of 3D printing. There has been some use of it for prototypes, but not in the forward flow manufacturing piece. Okay, super. So you'll be looking to hear a little bit of what Sean says in terms of the IMR approach and what we're looking to facilitate companies and organizations such as yourselves into that space, I guess. Yeah, absolutely. Okay. Well, look, I think Sean's presentation will give you a little bit of background in a very general sense about what we're at. He specifically goes through some of the equipment that we're looking at installing and maybe some of the capability we have here. I think it'll be a great introduction to what we're doing. And on the other side, you are into the simulation side, and it will take you through that process as well. So thanks, John, for that. Lovely to talk to you. Might just mute John again when we can. We're waiting on Donna McCarthy from Pfizer, I think, isn't it, Donna, as well? And we'll be good to go. We'll be good to go in the next minute and a half. And you can mute as people come on after we start talking. This would be good. Okay, good stuff. Good stuff. All right. Come on, Donna. You can do it, baby. Log in. Press the button. Good stuff. Nothing worse than dead time when you're here live in front of these companies, but still. We've got one more guy logging in. Once we get him up and running, we'll start the process. All right. 10:35. Come on, Donna. Yay. Hello, Donna. How are you?
Hi, how's it going?
Not too bad. Donna McCarthy from Mill Street. How are you, sir?
I'm very good. Yourself?
I'm all right, boy. It's a long time since I laid eyes on you, my friend. I've gotten older, but not that much, though, to be honest. Donna, you were on a... Yeah, like the rest of us. Come here, Donna. You were on a phone line there, are you?
I am indeed, yeah.
Do you want me to send you down the presentations so you can flick your way through them? Or have you got it? Have you got a copy?
I haven't. You can send it on, yeah, please.
I'll send it on. Donna, I'm going to put you on mute, right? So you won't be able to, we won't be able to hear you. It's just a function of what we're doing here, but we'll get that to you. All right, guys. Thanks very much. We're going to start this off. As I mentioned earlier on, we've got Sean McConnell from our additive group. Sean is going to take us through a presentation now on the work that IMR are doing, a little bit of background on that. Thanks, Sean. You can take it away.
Hi, everyone. My name's Sean. I work for Irish Manufacturing and Research on the AM side of things. So just real quickly, I'll just go through some of the stuff I've done and where my background is. So I'm working on IMR for the last 1.5 years as an additive research engineer. I've been in the additive space for the last 3.5 years. My main focus areas are that of design for additive manufacturing, how you can take what's been done the conventional way and add the most amount of value to it to really take the maximum amount of value from additive manufacturing and what it brings to the table. The AM system integration, so how you go about doing good stuff on machines and bringing that into your factory or workspace and taking advantage of it. Then also the applications of the development. So there's a lot of good work done out there with the OEMs, universities, etc. But how do we transfer that onto actual production lines? How we can produce proper, functioning, real-world parts? So that's kind of the application development side of things. So just a quick run through of a very, very simple what additive is, especially what our focus is. So we don't see it as a prototyping tool. We see it as a thing we use for high volume manufacturing. That is our goal, to get it into that kind of space. So with that, as all of you will know, there is a number of challenges, especially for a new technology such as this. So what you would do is, traditionally, what you do in additive is you create a 3D model. So with that brings its own set of skills you need to do such. And then from there, you will then build the part layer by layer in most additive processes, and then you would get a near net shape part. Now this is an extremely simplified version of what happens in real life, as there's many different factors, and that's what we're here to help with, addressing and helping with all them different factors. So what I'm going to talk about is what we're doing down in Mullingar in the new centre. So we offer a number of different things and how we can help that process. So first of all, it's additive manufacturing assessments. So there are all of you will have a portfolio of products, etc., and stuff it can be applied to, but it's very hard to determine where can you get the most value add. So what we will do is we will help you assess your products to see which ones are best for the particular additive application. And from there, we can also work on consultation, technical and business analysis. It's a new field. There's a lot of skills required. It can be hard to get up to speed. So that's where we can help in terms of helping you see that it's applicable, or what particular areas or niches within your own company can benefit from it. There's also the training for additive manufacturing. So even though the technology is 30 years old, as it's grown in the last number of years with a CAGR of 25%, there's become a massive skills gap in terms of people who can use the technology and the wide-ranging number of skills that are necessary. So what we're doing, we're learning ourselves every day that goes by what you need to know, what you need to do to take the most from the technology. So what we're doing is we're helping the next generations and even the current generations of engineers change how they think and train them for designing, for using, for handling additive manufacturing. We also do a lot of R&D. So like any machine or technology you buy off the shelf, it's off the shelf. It's not bespoke for your manufacturing conditions or your process. So within additive, there's a lot of space to optimize, whether it's laser parameters, material control, the design, etc. So we work on how we can optimize them things to get the most out of the machine. We also work on the material development process and the actual the process of getting the part through additive. So what that means is currently the materials is a large bottleneck for additive, and there's constant work going on to increase the material portfolio. So we deal with OEMs and academia in order trying to get comparable or better materials for additive. And then lastly, we are completely agnostic and unbiased. So whether you come to us with a problem, we will point you in the right direction if we can't help. So whether it's OEMs, other partners, academia, whatever the issue is, we have no problem and inform you what the best route is to tackle the particular problem you have. So what we have in-house, the fun part is the bit that makes me excited, what we actually have in the lab in Mullingar. So one of the key technologies is that of a carbon M2. This is a brand new technology. It's a kind of counterintuitive in the fact that it's a layerless production system. So instead of building the material layer by layer, it's a constant draw. So what that means is you can get material characteristics and properties that are directly comparable to injection molding. To the point now that a lot of companies are starting to replace their lower volume products with this technology. Now, but as it stands, there's very few of these machines in the world, so we're quite lucky to be the first one from a research point of view in Europe to have this machine. So we've got a lot of opportunity to add value to anyone who's interested in the technology. And on coupled with that, the materials it uses are far superior to traditional additive manufacturing materials. So there's a large area of scope for work there. Particularly, a particular example of that is how Adidas are now using it to produce a number of soles for their shoes that can't be produced any other way, and that's adding value to their business from that point of view. And they're scaling up to producing 100,000 in the next 5 years per year. So one of the other technologies have on the metal side is a Renshaw AM500. So this is a laser sintering machine that we're going to use to mainly focus on titanium and medical devices. So that's going to be the main focus of this machine. What's different about this machine that makes it unique for us, it's the first Renishaw IM500 PM system to be released globally. So we're quite lucky in the sense that we have the first one. What the PM stands for is process management. So what it will do is process monitoring. Sorry. So what it does is it allows you to view and take control of what goes on during the build, adding a deeper layer of quality control to the actual process. If any more information required on that, I'll be happy to help you. But until we get really hands-on with it, we want to get everything worked out first before we want to tell everyone how well it works. One of our other key technologies then is the EOS P396. So this is very similar to the Renishaw, but it works with typically a nylon-based powder. It has other materials available, but the portfolio isn't very robust. What is good about this machine, what it's typically used for, is low to mid-scale production. So there's been lots of studies and cases done where it can be comparable with injection molding up to 50,000 parts, given a certain geometric profile, etc., size, and your demands, size, scheduling, etc. So with that point of view, that's another key technology we have that we're doing a lot of work on to see if it is viable for our partners and anyone else that's interested. Also in-house, we have a number of other smaller technologies that each come with their own kind of USP in a way. So we have your material jetting machine that can build stuff with a very robust support, so it can do very detailed parts with nice features. We have a composite material extrusion machine that are getting quite popular as it's able to extrude Kevlar, carbon fiber, and fiberglass, so it can be used for quite strong purposes. We actually have a swinging chair house that's held up by parts in that machine. So luckily enough, our staff aren't too massively having broken yet. Hopefully that doesn't happen. And then we also have a number of form tube machines that for anyone that's interested in dabbing their hand in the end, I would recommend highly, because it is a cheap, effective machine that can do some really nice parts with a large portfolio of material. So we use that for kind of first iterations companies in terms of prototypes, etc. So that's pretty much what we have at the minute. I'll now take any questions any of you guys might have.
All right, guys. Thanks very much, Sean. That was very informative. I hope that that made sense. It gives you a bit of an idea of what we're doing here in terms of the capabilities that we're building in the car, and also, I guess, the opportunities that are available to you as our partners here in this. So we have a number of additional people in here. I'm unmuting you at the moment, okay? So please be aware you've got a hot mic. Everyone else can hear you. You are now live, as the man says. So does anyone have a question for Sean on this? Anybody at all? Give me your name
Sean.
first.
Sean, John Carmody here. Very good presentation. Thank you very much. You mentioned a number of the technologies that are there, and the constant draw system and the direct metal laser sintering. Do you have kind of a cheat sheet of the different technologies that you're working on and the different processes? And then I suppose my second question would be, you mentioned that I think it was the EOS, the nylon-based one, that's comparable with injection molding. Do you have, let's say, the time it takes to make a part? Do you have some comparisons against injection molding?
So for your first question, in terms of cheat sheet, yes. So we've developed a kind of a book, almost a book, nearly 100 pages of information there. It's not quite a cheat sheet, but it's a bit more comprehensive. But yeah, so there's 7 different types of technology defined, but given that it's moving every day, there's almost a new one coming out every week. So it's quite hard to capture everything. But in terms of the cheat sheet, yeah, you have one there. It's more than happy to share any information you need in terms of that. And in terms of the comparable injection molding, there is a number of papers written already. And from our point of view, we are currently working on that project at the minute to get a real-time value, because we found a lot of papers where they have the equivalent up to 30,000 are over 10 years old, and the machine we have is twice as fast. So we're very anxious to repeat that research in a way to see where the state of affairs is now. And in terms of the OEMs, they can happily provide you what they reckon it can compare with, but personally we prefer to do our own tests to get real-world results for companies from their own actual products.
And John, I suppose to answer your question there, we're developing out training modules. We ran training courses last year. I think there was 50, 60 companies at them over 3 days. IMD or Yeah, the IMDA, we're developing a skills net program which we won last month. So there's quite a lot of information here. I think, John, that we can help you with. Any other very quick question? I've got about 60 seconds left on this one. Otherwise, we can bring you back. Anybody else? Going, gone. Okay, guys, we're going to. Thanks very much, Sean. Really appreciate that. It gives you an idea of the depth and, I suppose, the seriousness of what we're doing here in IMR across the various elements. So I'm going to put everybody on mute. You're all going to be muted again, so you can start talking about us and discussing how well I look and so on. We're now going to introduce Dr. Anna Rotondo. Now, Anna is with us on the simulation side. She's a wonderful here we have. We're very, very lucky to have the researchers that we have in this organization. And Anna, if you'd like to come over and take your step for 10 minutes. Thanks, Anna.
Good morning, everyone. So, as Andrew said, I'm Anna Rotondo. I work as a optimization and simulation scientist here at IMR. So I hold a management engineering master's degree from Polytechnico di Bari, and I completed my PhD in manufacturing engineering in Dublin City University. I worked there as a postdoc for 5 years. I was involved in real-world industrial problems through national and European projects, and they were all based on simulation-based optimization. I joined IMR in 2015, and I really love numbers, and I love playing with numbers and anything that has to do with numbers. So what is simulation? I'm going to talk about simulation a bit today. And simulation has been defined as the next best thing to observing a real system in operation. And it basically offers a risk-free environment to understand the behavior of the system. So how does the system work, and predict the future behavior of the system, so what is going to happen next, and also evaluate alternative strategies to operate the system. So what happens if? So I'm going to talk about the simulation process because I think the simulation process is interesting in itself, apart from the benefit we can gain in terms of performance indices. So a simulation process starts by defining a specific case scenario in which we're going to work. And after that, once the problem is well defined, then we are going to look at the data relevant to this problem, analyze them, try to get to know the system to be modeled a bit better. So we're trying to build a progressive knowledge on the system to be modeled. This would allow us to develop conceptual models that are going to be validated. And then once we have a good understanding of the system, we can start building actual models and get them to a point where they are accurate enough to replicate reality and conduct experiments. So then we do our experiment analysis, try to optimize the system using the model we have. And when the model is built, it's built in such a way, but we hope to build in such a way that it's generic enough to be transferred to other cases and to be scaled to bigger problem instances. So we're going to look at some aspects of this process in more detail. So we look at a specific case scenario. I'm going to refer to a project we done a while ago. It was about batch number tools optimization. Batch number tools are very complex tools that have an internal robot that moves batches or items around to different chambers according to a production recipe. In this case, the chambers were actually tanks filled with chemicals and water, and as most of the chamber tools available, the scheduling software was proprietary to the vendor, so there were very little changes that we could do directly on the scheduling logic of the tool itself. So the project was about how to assign batches to identical tools operating in a station in a way to optimize, to run the tools more efficiently in terms of cycle time, so improving productivity in the system, but also looking at environmental implications of the tools management in terms of chemical waste reduction and also water reduction. So as the next aspect, we're going to consider the system knowledge process. I start with awareness that the experts on the system are people working in the system on a daily basis. So operators, frontline engineers, and managers. And so what I try to do is to encourage knowledge transfer between system experts and the simulation, so myself. And of course, this will trigger processes of knowledge gaining for the system experts themselves, because usually simulation is not familiar with the system, so it's going to ask questions, and these questions are going to trigger investigations from the system expert to get detailed answers. And the same, the knowledge transfer is encouraged between the system experts themselves, because there are people coming from different departments or different systems that are brought together in meetings, so they have the opportunity to exchange opinions on how the system works. And also, as part of this process, an important aspect is to avoid a myopic vision that a system expert can have on the system, because he's so used to follow consolidated practice. A case of this is, referring back to the project I mentioned earlier, there was a waiting area in the tools that was deemed as a bottleneck by the industrial engineers working with the system, because they thought that once the waiting area was occupied by a batch, no other batch could be loaded into the tool and transferred to other tanks. And this was not the case. And it was easy to find that out just by looking at the data and analyzing the data. But of course, engineers were not, they didn't have time to conduct this type of analysis. And then another case was about preventive maintenance of the tools. So all the 5 tools operating in the station were shut down at the same time, thus causing some sort of cycle time variability that could be avoided just by staggering the preventive maintenance operations. So the other aspect is the model development. We have a list of possible optimization and modeling approaches to be used. And the idea is just to communicate that we are really spoiled for choice. And the simulation can really help in this process, because it's probably more familiar with these techniques than a system expert. And it can choose then the most effective and efficient approach to model the system and get answers out of these models. So the idea, at least from the way I approach the problem, is to keep complexity to a minimum, because an easy model is a model that can be managed more easily, and is a model that provides easier answer to interpret. And we should always try to keep the level of detail at a minimum, and the detail should be functional to the objectives and not the other way around. So there is no point of having a very detailed model if the detail is not going to add any additional information to the answers we are seeking. And once the model is built, then we can progress with the experimental phase. Just to give you a flavor of what sort of results can be achieved by a simulation project. Once that model of the batch number tools was built, so I was able to play with parameters, scheduling parameters, and this actually brought to a 74% cycle time reduction obtained on the floor, so, which was a great result, obviously. And the model also predicted a 25% average makespan reduction when the sequence of batches was optimized, the sequence of batches to be sent to different tools. And another thing I did with that model was try to optimize the assignment strategy. So the logic with which the different tools in the station were chosen to process the next batch. And on top of this productivity improvement, there was an estimated savings in terms of chemicals from 3 to 5%, which corresponded to thousands of gallons per day. This was a multinational company. And 1 to 2% cost savings as well. So the message I just want to get across today is that every time we're faced with questions of the likes of how does the system work, or what is going to happen next, or what is going to happen if I implement a strategy, then simulation can really provide you with an answer. And simulation in the manufacturing field is not just about productivity objectives. There is lots of studies about bottleneck analysis, plant layout, planning and scheduling, but we could also look at many other objectives, many other aspects, such as the environmental impact of manufacturing policies, marketing strategies, how to optimize them, how to optimize the recruiting policies. Also, if we want to manage worker seasonalities, for instance, if you're faced with such a problem. And we can look at quality aspects in terms of customer satisfaction and quality control. And simulation is not just about multinational companies. Of course, numbers for multinational companies will be bigger, but we could also look at SMEs. And there was a project a while ago here in IMR about an SME. It was about optimizing the floor space layout. So we can really work with any company and can look at any type of objective. So if you have any question, I'm happy to answer.
That's super, Anna. Thank you very much. Well done. I think you get a feel there from Anna for the vision, the breadth, the depth, and certainly the excitement in that space. And I love the first line where Anna says, "I really love numbers." I am numerically dyslexic myself, so I'm very impressed with someone of Anna's ability. I'm unmuting you at the moment just to let you know that your mics are live. We have control of your internal systems. We can hear what you're saying about us. So if you'd like to ask Anna a question, I'm aware now that we're down to the last 2 minutes here. Does anyone have a question that's beating on their systems, please? Just speak up, give us your name, and we'll do our best to facilitate you. Anyone?
Yes, I have a question. It's Paul from Bombardier Aerospace.
Hello, Paul. Please, what's the question?
First of all, Anna, very good presentation and some impressive savings there on that project. I'd just like to know, obviously you're using different software. How do you assess the software before you use it? Software can be very expensive. There's good simulation software out there, and there's also software that's underdeveloped and maybe not effectual or effective. How do you go about assessing the quality of the software before you use it?
Well, I think it depends on the problem to be analyzed, but there is lots of open source software available as well. So it depends on if you want really nice visualization features. Of course, commercial packages are much better, but if it's just about performing a what-if analysis, then I guess any programming language can be used. So the cost can be kept on minimum in that case as well. So it's of course it depends on the objectives, on the analysis, and as I said, the fact that you want to visualize the results in a better way, or that's not needed. So I think that every time we conduct a project, we do that as part of the process. Just try to understand which algorithm or software is going to work best based on your requirements.
Paul, do you have a very specific question that in terms of what you were doing up there in Bombardier, or is it just a general sense of how we evaluate the packages we're using?
Well, my question is based on experience in that we have a particular process here that we use, and we find that we've used software in the past that wasn't accurate and wasn't up to the standards we required. So I was just wanting to know, was there a particular process for identifying software for a particular application, or a stepwise approach as to how that would be done?
Well, based on my experience, most of the simulation packages I've used are very, very similar. So I guess it's more the way the model is built that can make a difference. So that's why I think it's important to have an expert that guides you through the process of building a simulation model, because there are software that can make great things, but if the assumptions or if the way the model is built is not the best way, probably, then of course then you can see the faults in the software. But I guess it's more about the way of building the model than the software itself. Super
stuff. Paul, thank you very much for the question. I think maybe that might open up a conversation offline just to align ourselves, if that's acceptable, in terms of your strategy there, and certainly our experiences here across multiple different formats and different organizations. Guys, we're running out of time. Thank you for your participation this morning. I think it's important at this point. I think we've had 8 different presentations over the last number of months across various platforms and various technologies and various capabilities internally. We'll continue to do this into the end of the year, and then we'll look at a review to see what works best. But particularly this morning, there is a strong capability and a footprint, and quite a lot of funding nationally gone into the program in Mullingar. It's beginning to build out as something very, very interesting for organisations such as yours. And I guess it is important for you guys to get involved in that process. And equally on simulation, some of you are using it quite extensively, some of you less so. We'd encourage you to contact ourselves, particularly Anna here, and we'd be delighted to help you as members along your journey in that space. Guys, thank you for your time, very much appreciated, and we're over now tonight. Thanks, guys. Thanks.
Thank you, Fergal.
Bye.
Cheers.
Bye.
Not at all, guys. Thanks very much. Really appreciate it. Enjoy the weekend.
You too.